Yeah, we have so far concentrated on dynamical systems which are generally nonlinear, with special reference to systems which are deterministic, in the sense that there were specific rules of evolution, and then we looked at the nature of the solution, the dependence on the initial conditions, and sensitive dependence in the case of chaotic systems. We looked at both differential dynamics, where systems were described by sets of differential equations of the first order, coupled first order differential equations, and discrete time systems, where the dynamical system was described by a map of some kind, a recursion relation, which gave the rule for evolution in time. But you see, in real life, most systems that we deal with would also have influences from outside or even internal sources of noise, which can't be given detailed descriptions. You can only give statistical descriptions for such influences, and then the resulting equations that you have no longer are deterministic equations, but they would involve components which are random, some kind of noise which is imposed on the system. So the general dynamical system would have portions which are deterministic and portions which are pure noise with some specified statistical properties, and this would lead us to the area of stochastic differential equations and stochastic difference equations and so on. We haven't considered that very much in this course, but I'd just like to introduce you to the very elements of stochastics so that you can make some contact with what happens in real systems, some of the typical noises that one deals with. Now, of course, we also took a little excursion into probability and a little bit about Markov processes and so on. So we will build upon that knowledge and try to go on from there to write down the most elementary stochastic differential equations. Here is one instance of where it can happen in a practical situation. You know that if I have a set of chemicals reacting with each other, in general you would have the concentrations of these chemical species, the different molecular species, as your dynamical variables, and you would perhaps have a set of differential equations of the form, if the concentrations are of the form C1, C2, etc. at some given instant of time, then you would perhaps have a description for the way the reaction proceeds in terms of differential equations which say C1 dot equal to some function of C1, C2, etc. and so on for the remaining concentrations. So this would give you a very gross description of what happens in the system, and one of the ways you would write down these functions is to write the individual reactions down and then use perhaps the law of mass action along with the rate constants to tell you the rate at which the concentration of each species changes. Now that is a dynamical system in the sense we have understood it, a set of coupled first order differential equations with possibly some nonlinear terms on the right hand side. And then the question would be, is there an equilibrium, is there an attractor, etc., etc. What kind of steady state or equilibrium solutions you can have for such systems. That would be one brand of questions. But of course you could also look at this at a more local level, and you could say, well, perhaps the concentration Ci of the ith species changes from place to place if you coarse grain the system, and it is a spatially extended system, in which case this becomes a function of R and T. Then you could ask, how does this change as a function of time, and typically you would get equations of the form delta over delta T of this would be equal to, again perhaps some function of all the concentrations C1, etc., some deterministic portion which would be governed by maybe the law of mass action or whatever the set of reactions concerned gives you, plus there could be diffusion of this species, and that would be described perhaps by writing a diffusion constant I for the species I times del squared Ci as a function of R and T. Notice that we haven't put in any noise here at all. This is still a deterministic system, but it is spatially extended. So these are partial differential equations, and now you have a much more complicated problem than before, because you have a degree of freedom corresponding to each of the species at every point in space. and so this certainly is much more complicated than the earlier kind of system that we talked about. These are called reaction diffusion equations. And their solution poses several challenges. You now really have to deal with a much more complicated system of partial differential equations of this kind, okay. But it is still not a stochastic differential equation, it is still completely deterministic. You could say, okay, I do not have something as regular as this, but I have noises, I have perturbations, external forces and so on, in which case you would have genuine stochastic differential equations. Let us look at the simplest of these. So let us now change horses and go and look at the simplest kind of stochastic differential equations that one could possibly have. So I start with extremely simple examples of such equations, and then we go on from there to look at more complicated things. And let me in fact use an example which is familiar to all of you, the example of a fluid, say an ideal gas like the gas in this room, and try to write really a microscopic equation for a single molecule. We assume this to be completely classical, and I try to write a differential equation or its equation of motion including the effects of collisions due to the other molecules, and try to see where this gets us, okay. Now what would you say? Obviously if I took a simple system of this kind like an ideal gas or a simple fluid, and I write Newton's equation down for a given molecule, we will assume these to be ideal point particles, point masses, then let us make life even simpler by focusing on one particular Cartesian component, say the x component of the velocity, and then what you write is to say the mass times dv over dt, this is the acceleration, is equal to the force on this particle. And the simplest assumption you could make is to say that I focus on one particular particle of a system like the gas in this room in equilibrium, which is in thermal equilibrium. So I know there is a Maxwellian distribution of velocities, and then I try to write down a microscopic equation of motion for a single particle, given tagged particle molecule. This is equal to the force that acts on it. So let us write this as the force, and this force of course would depend on the time, it would change from time to time. This is some time dependent force here in this fashion. And what would you say this force is equal to? Well, it would be the vector sum, we are talking about a single component, so it would be the resultant of the external force on the system, if any, maybe you have got it in a gravitational potential or an electric field or anything like that, some external force if any, that could of course change with time, plus the internal forces due to the system itself on the particle. And this would come due to the interaction of this molecule with all the other molecules in the gas or in the fluid. And we are going to make a very simple assumption and simply say, for the moment you can always handle something with an external force, let us do something in the absence of the external force and ask what kind of internal force you have here. So now this internal force, since it is due to all the other molecules, and I am going to now simply assume there are just elastic collisions, that happens at completely random instants of time, and so a simple assumption would be to say mv dot is equal to, without this external force, an internal force there, and it is a random force of some kind. And let me call that random force eta of t. So this is a random but it is not enough to say that it is random. The moment I say something is a random variable, I have to specify statistical properties of this random variable, otherwise I can't do anything more. So we have to now start saying what kind of force is this, what kind of random force is this. We make the simplest possible assumptions. This force is changing extremely rapidly because on the average the molecules in this room, each molecule undergoes collisions such that maybe the time between collisions, the mean time between collisions is of the order of picoseconds. So certainly within any measurable time of even a microsecond, it has undergone a large number of collisions completely, and its motion is totally randomized. So one possibility is to say that this force here, a very reasonable thing to say is that the average value of this force is 0 at all times, because the gas as a whole isn't going anywhere, therefore the average force is 0. It is a reasonable assumption to make, independent of time, simply 0. You could also make the assumption that this force has no memory at all. The different collisions, it is very unlikely the same two particles keep repeatedly colliding with each other, recollisions are very, very improbable. So a very reasonable assumption is to say under these circumstances that this force is completely uncorrelated. What happens from one instant to another, they have nothing to do with each other. So a reasonable assumption would be to say that eta of T1, eta of T2, two different times, this thing here, it factors into a product of eta of T1, average of eta of T1 times average of eta at T2, because they are uncorrelated with each other. When two random variables are uncorrelated, then the average of the product is the product of averages, since they have nothing to do with each other. So this thing here is 0 for T1 not equal to T2, and of course when T1 is equal to T2, this thing here is a non-zero number. It could even be unbounded, because we have in mind something of this kind. If I plot this correlation function as a function of the time difference between T2 and T1, I would expect that if T2 is bigger than T1, I would expect that this thing comes down and goes off like that. Physically this is what I would expect, such that the whole area under the curve is finite, because that would specify a correlation time. So a crude assumption, a zeroth order assumption, is to say if I look at this force on some time scales much larger than the characteristic time scale of the decay here, this thing looks like a delta function to me, and therefore a good assumption is to say this is equal to some gamma of delta of T1 minus T2. This is a white noise approximation. This simply says that the force eta is delta correlated, there is no memory, 0 memory time, and gamma is some constant. I have yet to determine this, but it is some kind of constant here at the moment. So it does satisfy the requirement that it is 0 when T1 is not equal to T2. Moreover, we have seen earlier that in the case of a stationary random variable, in other words a random variable whose statistical properties do not change with time, the average value is independent of time, and that is satisfied here, it is certainly 0, and the correlation function is a function not of T1 and T2 separately, but a function of the time difference T1 minus T2 or T2 minus T1. In fact it is not hard to show that it is a symmetric function of the time difference. That is because you can subtract from each of these time arguments the same amount of time. If I subtract T2, then this becomes eta of T1 minus T2, eta of 0 here. If I subtract T1, then it becomes eta of T2 minus T1, eta of 0 here, but these are classical variables, you can commute them in either order. Therefore it is easy to see that as a function of T1 minus T2 it is symmetric. In other words, it is a function of modulus T1 minus T2, and that is exactly what the delta function is. This thing here is symmetric under the change of sign of its argument. So this is a good model as it stands. We still have to see where it gets us, but this is a good model. Now if I make these assumptions, look at what is going to happen, what consequence we have immediately. It is an extremely simple model, but we must try to see what it does for us. So I start again with the equation of motion with these statistical properties, and now I ask, what does this imply for me? What kind of average behavior will this imply for the velocity? But remember that now I have to specify initial conditions. To solve a differential equation I have to specify initial conditions. That is easily done. The solution of this equation, the formal solution of this for a given initial condition, so given the initial condition V of 0 equal to V naught, so I focus on some particular particle whose velocity at t equal to 0 happens to be v naught, and that is a specified initial condition, and I ask what is the fate of this particle, of this molecule. For this initial condition, this equation implies that v of t is equal to v naught. If I integrate this equation out trivially, it is v naught plus 1 over m integral 0 to t eta of t1 dt1. I simply integrate this equation. Now that is the solution. Remember, the system is in thermal equilibrium, so I know that there is an equilibrium Maxwellian distribution of velocities. So I already know that there exists an equilibrium distribution P equilibrium of V, which is e to the minus mv squared over twice k Boltzmann T, normalized appropriately. The normalization constant in this case is that of the Gaussian, so it is 2 pi kt to the power of half. So that is the probability density function of the velocity in equilibrium. That is the Maxwellian. Maxwellian distribution. It should really be called the Maxwellian probability density function, but of course in physical applications we very often use the word distribution to mean the density function. Instead of the cumulative distribution function, we just call it distribution. So I know that, but remember, this is a conditional quantity here. If the velocity is found to be v naught at t equal to 0, then the velocity at time t is given by this thing here. And now I average over the entire system over all those particles whose initial velocity is v naught. So essentially I average over all realizations of this random noise, and let me call that average denoted by an overhead bar, because it is an average conditioned upon the fact that the initial velocity of whatever system particle I am looking at is v naught, some given v naught. Later I will relax that and average over all possible v naughts as well with the Maxwellian distribution. So what happens here if I do this? This implies that the average value of v of t, for which I denote use an overhead bar, is equal to v naught, because this is a given number, there is nothing to average over, it has nothing to do with the noise, plus the average of this quantity here. This is an integration, it is like a summation, and averaging is also an arithmetic summation procedure. So they commute with each other, and the answer is this is 1 over m times the average value of eta of t1 dt1. But we saw that the average value is 0, we assumed that it was 0, and therefore this is it as it stands. But this is already extremely unphysical, because it says if I start with a particle with velocity v naught, then these particles, that subset of particles which start with velocity v naught, remain with the velocity v naught on the average for all time. That is clearly not true. It's clearly this is unphysical, so something is wrong somewhere, and we will see what is wrong, but you see we still have to discover where we went wrong. So it looks very reasonable that all we said was this thing here is due to all the other particles and they are completely randomized very fast, but then if I take this conditional average, it leaves you with just v naught here. So we already begin to see there is something wrong here, but let us see what further it says. We also find that if I square this, yeah. Why should this velocity be the same? I would actually expect, why should it be so? Why should it remember its initial velocity? I start with the set of particles whose initial velocity is v naught, and now I discover that their average velocity remains v naught at all times. On the other hand, if v naught is very far from 0, I expect that the average velocity should actually be 0 according to this.
But the force which is going to be in operation here is going to be some random force.
Yes.
It could be positive, negative.
Yes.
So over a period of time it accelerates and decelerates.
So therefore I would expect it to go to 0. That is precisely the point. I would expect things to go to 0.
So the change of velocity is 0, so it remains at 0.
No, if this v naught happens to be extremely large positive, I wouldn't expect it to remain that, I would expect it to transfer momentum to other particles and slow down. I won't expect that it remains as it is, because in an elastic collision, take it in one dimension, in an elastic collision between two equal mass particles, their velocities actually get exchanged.
But you don't model that. You say when you model a random force, all that doesn't get modeled.
That's the problem. That's exactly the problem. So it's going to tell us that this is, it's going to get worse, and let me do this and show you what's going to happen here. Let's find the square of t, v squared of t. What is this going to give us? Well, first there is a v naught squared, and then there are two cross terms where this multiplies that and vice versa, but this is a constant and the average of eta is 0, so those things go away, plus 1 over m squared integral 0 to t dt1, 0 to t dt2, eta of t1, eta of t2 averaged over all realizations of this noise, subject to some initial, the tagged particle having a velocity v naught, but that has nothing to do with the noise here. This is a large heat bath in which you have your tagged particle sitting, and therefore this bar here is exactly the same as far as eta is concerned as the full average over the system, and that we saw was gamma of delta of t1 minus t2. So let us put that in, and this gamma comes out and you have a delta of t1 minus t2. But this integral is trivial to do, just says replace t1 by t2, and that is the end of it. So this integral goes away and you are left with this, which gives you a t. Now if you go back here, from this distribution we know the following, we know that v in equilibrium is 0, because this is a component of the velocity, it is an even function of v, and therefore we know the average velocity is 0, every component of it is 0. We also know from this Gaussian, it follows trivially that this is kbt over m, which is just a verification of the fact that 1/2 mv squared average is half kt, which is in accord with the equipartition theorem. Every degree of freedom, translational degree of freedom, has an energy half kt on the average in non-relativistic free particle situations. But what is this telling us? This is crazy, because if I now define 1/2 m this to be the average energy, if I multiply by 1/2 times m on top, sorry, so this goes away, and this gives me the effective temperature of the system, then it simply says you leave a beaker of water alone in contact with a heat bath and its temperature spontaneously increases to infinite values given enough time, which is clearly absurd. So not only was this bad, this is disastrous. Where are we wrong? Where are we wrong? Of course you could immediately question this, the assumption made on eta, and say, well, eta of t cannot be delta correlated, because that is unphysical. It says that the correlation time is 0 and there is no physical force whose correlation time is 0. It could be very, very short, but it can't be 0 strictly. This is true, but on the other hand we have managed to separate time scales. I tell you as a matter of hindsight that the actual correlation time of this random noise would be like the correlation between the time between collisions, that is of the order of picoseconds or less. On the other hand, if I look at the system on the time scale of microseconds or more, then this is certainly a good approximation, it does not matter at all.
The force is not random.
But the force is, it is random, but there is something missing in this random force, and a moment's reflection will tell you that if a molecule has instantaneously a very high positive velocity, it is clear it suffers more collisions per unit time retarding it than pushing it forward, and therefore the right thing to do is to go back to the model and say that mv dot is not equal to eta of t alone, but also has a systematic part which retards it, which is proportional to its velocity, instantaneous velocity, but is in the opposite direction. and that is best modeled by saying it is minus on this side something proportional to the instantaneous velocity with a constant gamma say. I would like to make this constant gamma have the dimensions of time inverse, so let us put an m here. This is also random. Why? Because this is a random driving force that makes the velocity random, and therefore this is also random, but it is a systematic part of the random force. It is a specific function of the output variable, and we made an assumption. We have said that this retarding force is linearly proportional to the velocity, instantaneous velocity itself, and that of course immediately tells you that v dot plus gamma v is equal to 1 over m eta of t in the absence of an external force. You could of course always add an external force to this, but this is the solution in the absence of an external force when the system is in thermal equilibrium. And what is the solution to this? This equation, and gamma is a positive constant, that is crucial. Now what do you think is the solution to this equation? Well, all we have to do is to solve this first order linear differential equation with that initial condition instead of this thing here. All we need to do is to put in the integrating factor, which is v naught e to the minus gamma t on that side, and since the integrating factor is e to the minus gamma t, in this case this gets multiplied by e to the minus gamma t minus t1 dt. That is the solution which obeys this boundary condition, the initial condition. Right?
What made you decide on this model?
You could put in other models, but this is the simplest thing. What made me decide on it was simply experience based on what happens in a fluid. I know that the friction for small velocities is proportional to the velocity itself. That is the assumption I made, and it is directed oppositely. This is called the Langevin equation. And where does it get us? Well, for a start, please notice what happens to the mean here. It is this term here, it is not that, that goes to 0 because the average of eta is 0. So indeed you have this. What happens to this at t goes to infinity? It goes to 0, so we seem to be on the right track, we seem to be getting back equilibrium, but we have to still check this out. So this goes as t tends to infinity 0, which happens to be this. We have further corroboration for that, because how would I compute the full average of V? The full average of V of t would be this average averaged over all possible V0s, because this is a conditional average, it is an average over that subset of particles whose initial velocity is V0. I take that subset and I use all realizations of the random force eta of t, but now I would like to get a full average velocity, it does not matter what initial condition I choose. So do you agree that this quantity here is equal to dV0 V of t bar over all possible values of V0 with what weight factor, with what distribution? With the Maxwellian, because the system was in thermal equilibrium to start with at t equal to 0. So I put in P equilibrium of V0, and what do you get for this integral? This is from minus infinity to infinity. Well, notice this is V naught e to the minus gamma t, e to the minus gamma t does not figure in the integration. This is an even function of V0, you put a V naught, so you get 0 straight away. So actually we seem to be on the right track as required. So it is actually restoring V equilibrium, but there is another lesson we have learned from this, it is a very important one. To find this V equilibrium I can do in two steps. One of them is to find the partial average over a subset whose initial condition I prescribe, and then I either average over all the initial conditions or I simply wait for long enough. I do not average over all initial conditions, I say I do not care about the initial condition, I wait long enough and the system forgets its initial condition and indeed it goes to 0. My initial assumption is that a system is in thermal equilibrium with a Maxwell distribution of velocities. That follows from equilibrium statistical mechanics, independent of this time dependent stuff completely. This thing here, I would like to find the average of the velocity of the particles in this room at any instant of time, and I start by saying at t equal to 0 the system is in thermal equilibrium, I do not do anything to it. Now I know the average value must remain unchanged with time. Now I am trying to build a model for what happens if I ask time dependent questions, namely if I start with a particle whose initial velocity happens to be v0 and I watch it, what can happen to this on the average? Well, this model tells me its average velocity will decay from v0 to the value 0 given enough time with some time constant gamma inverse. But I could be impatient, I could say no, to find this average value at any instant of time, given the fact that the distribution is known at t equal to 0, all I have to do is to find the conditional average, the partial average for a given initial condition and then average over all initial conditions with the equilibrium distribution. So either I let t go to infinity or I let this happen and I must get the same answer. And the reason is I expect that if this process by which this whole thing is happening is a mixing process, I expect that the conditional probability density that the velocity of a particle is v at time t, given that it was v0 at time 0, this thing here I expect that as t tends to infinity this memory is lost and I would expect this to go to p equilibrium of v. Right? But if that happens then the averages should also follow the same rule. I would expect that if I wait long enough I should get the equilibrium average in this fashion. So this is what we have to corroborate whether this happens or not. Well, it seems to work at the level of the mean, but the real test is at the level of the mean square because that is what involves physical quantities like the energy, average energy of the particle. So let us try to find this quantity now, v squared of t, and where does that get us in the Langevin model? Well, this is equal to, I have to take this solution, square it and then take the average value. The first term will be very trivial, it is v0 squared e to the minus 2 gamma t, as I square this guy, plus a quantity which is the product of this times that averaged over eta, that is 0 because the average of eta is 0, and similarly in the other direction, plus a 1 over m squared integral 0 to t dt1, 0 to t dt2, and then e to the minus gamma t minus t1 e to the minus gamma t minus t2 times the average value of eta of t1 times eta of t2, but that we have a Langevin, we have a model for it in this white noise approximation, which is nothing but gamma over this times a delta function of t1 minus t2. Yes. We have to do this slightly more complicated integral, but that is not hard because it's the integration region is symmetric, both of them run over the 0 to t range, and so the region of integration is a square on which you have to integrate on the 45-degree line which corresponds to t1 equal to t2. So this means you simply replace t2 by t1 everywhere, get rid of this, and this becomes a t1 which just gives you a factor 2 here, this goes off, and I pull out and this integration is gone. I pull out e to the minus 2 gamma t and I have e to the plus 2 gamma t1, and that is e to the 2 gamma t1 minus 1 divided by 2 gamma, right. So this goes away and I get a 2m squared gamma and I get 1 minus e to the minus 2 gamma t. That is it. So where does that get us? It says v squared of t conditional average is gamma over 2 m squared gamma plus v naught squared minus gamma over 2 m squared gamma e to the minus 2 gamma t. Now we can do two things. One of them is to let t go to infinity and see what happens. So if you do that, this is just gamma over 2 m squared gamma, just a constant of some kind. On the other hand, if I take this quantity and I do v squared of t, that is equal to integral dv naught v squared of t bar p equilibrium of v naught. I could also do that. I could also average over all values of the initial velocity with the Maxwellian distribution, which we have assumed is valid at t equal to 0. What happens here if I do this? This is just a constant, so this part does not average to anything. That is a constant, does not average to anything. What happens to this? What is the average value of the initial square of the initial velocity over the Maxwellian distribution? That is of course given by the equipartition theorem. So half m v naught squared average is kt half kt. So v naught squared average is kt over m. So therefore this thing here would give you gamma over 2 m squared gamma plus k Boltzmann t over m minus gamma over 2 m squared gamma e to the minus 2 gamma t. That is the result. I would like this to be equal to this. If the system is in thermal equilibrium, I would like the two to be equal. I am not using the equipartition theorem, I am simply saying, be very careful, I am saying in equilibrium statistical mechanics, the principle of equilibrium statistical mechanics tells me that when a system is in thermal equilibrium, then for an ideal gas or a system of non-interacting particles of this kind, the average value of the kinetic energy in any component, the average value of half m times the square of the velocity, any component of the velocity, is half kt. I am not using any equipartition theorem. I know that the distribution is Maxwellian. That is an equilibrium distribution. It is the canonical Gibbs distribution, and I know that from equilibrium statistical mechanics. So that is an input automatically. Now I am asking time dependent questions which are outside the purview of equilibrium statistical mechanics, and therefore I need to have a specific microscopic model, and the model that I have chosen is the Langevin model. But this has to be consistent with equilibrium statistical mechanics. So I am not doing anything to it, I am simply taking the system in thermal equilibrium, focusing on a particular particle at t equal to 0 and asking time dependent questions of this without changing the thermal equilibrium situation. And it is clear these two must be equal because the system has not been affected at all. What is in thermal equilibrium should remain in thermal equilibrium. This quantity should be independent of time, and this should be equal to kt over m. When is that going to happen? If I equate this to this has got to be 0. There is no other way the time dependence can be got rid of. Moreover, the answer has to be kt over m, and that magic is obtained simultaneously. Not only does this vanish, if this is equal to that, but this coefficient also becomes kT over m. So you have complete consistency provided only that this be equal to that. So what does that tell you finally? This is possible, it is consistent, this Langevin model is consistent with equilibrium statistical mechanics if and only if consistency, if and only if gamma over 2m squared little gamma is kT over m, or if I take it across to the other side, is equal to 2m gamma k Boltzmann T in the Langevin model. So what have we achieved? What has happened here finally? This quantity was put in phenomenologically as a friction constant in the systematic part of the random force. This quantity here was put in as the strength of the random part of the random force, truly random part of the force, the molecular collisions. This measures the strength in some sense because it figures it is the coefficient of the delta function which is in the autocorrelation, and it says the strength of the fluctuations as measured by this gamma, the fluctuations in the random force due to molecular collisions, must be related to the damping coefficient. So you can't have arbitrarily large fluctuations for a given damping coefficient and vice versa. The stronger this is, the stronger that is too, to preserve thermal equilibrium. And this is a relation, it is the first example of a very deep relationship, it is called the fluctuation dissipation. Or theorem. It goes by many names in this version, it is called a Nyquist relation in the theory of thermal noise in a resistor due to Brownian motion of the charge carriers. This is precisely the sort of relation you get between the power spectrum of the voltage, the random voltage, and the resistance that you have here at any fixed temperature. It is exactly the same relation. But once you put that in, now that is input for consistency. We are guaranteed now that the system is consistent with equilibrium statistical mechanics. So once that is taken care of, then we can actually go ahead and compute averages. We can compute all kinds of averages now. So this is the first crucial point. You have to put this in as a condition on the Langevin equation. Okay. Having done that, let us now see what P itself would be. How would we get at what the probability distribution itself is? So what is P of Vt given a V0? I will drop the 0 to show the instant of time. I will drop this and ask what is this guy equal to? Well, I need an equation for it. I need to make some assumptions. It turns out that if I make the assumption that the velocity is given by the Langevin model, the Langevin equation, and eta is what is technically called a stationary delta correlated Gaussian Markov process or a Gaussian white noise, then it turns out that this process V as described by the Langevin equation is a Markov process in itself. It is not delta correlated, it has a specific correlation time which we will find out now, but this conditional probability here satisfies a master equation characteristic of Markov processes, in this case a very simple Fokker-Planck equation. But we will write the solution down, go back and look at the Fokker-Planck equation. I am going to write the solution down by assuming that eta of t is a Gaussian white noise. So eta of t, a stationary Markov delta correlated with 0 mean. That is the technical assumption. So it is reasonable, because it is reasonable to assume that the statistical properties of the molecular collision, force due to molecular collisions, does not change with time. Reasonable to assume that it is delta correlated on the time scales we are looking at, it has got 0 mean, that is physically reasonable. We are going to make the technical assumption that it is Gaussian. Namely its probability distribution function, the density functions are all normal distribution, they are all Gaussian distributions. Now that is a technical assumption, but there are reasons to believe that that is also a plausible assumption based on the fact that this eta is a resultant of a very large number of uncorrelated events. So something called the central limit theorem comes to our aid, and therefore this is not an implausible assumption, it is probably it's the most likely thing. Okay. The fact that it is Markov, that is an assumption. We want to make an assumption that this is completely uncorrelated, it's a very short time memory, one step memory. That is a technical assumption. You could relax it, in fact in real fluids you have to relax it a little later, but that is the simplest assumption to start with. Given this, and given the Langevin equation which says V dot plus gamma V equal to 1 over m eta, and eta has these statistical properties, it turns out that V is also Markov, it is also stationary, it is not delta correlated, it has a finite correlation time which in this case will turn out to be gamma inverse, but it also turns out to be Gaussian. So it will turn out that the Gaussian property remains, it is very robust under this equation. So the driving variable is Gaussian distributed, so is the driven variable here. If you grant me that, then I could actually write down this thing here, this conditional probability density function, because you know that a Gaussian process, a Gaussian random variable is determined, its distribution is determined by two parameters, the mean value and the variance. Those are the only two things you need. So let us compute those quantities here. We can actually write down what these quantities are, because to start with I am going to require the following on this P. I am going to write it down by hindsight. So at t equal to 0, what is this density function? It says this is the probability that the velocity is some v at time t, given that it was v0 at t equal to 0. So what is the initial condition on this guy? What does that imply for this? It has got to be 0 unless v equal to v0. It is a Dirac delta function, it has got to be normalized to unity, so it is a Dirac delta function. And what would you expect this to become as t tends to infinity? No, the probability density function, the Maxwellian, nothing is happening, so I would expect this to become P equilibrium of V. Must check out that my solution in fact does so. And then if we have knowledge of what the mean value is and what the variance is, then we can actually solve the problem completely. But we do have that knowledge, because I know that V of t is V naught e to the minus gamma t, and I also know that V squared of t is equal to that thing there, this quantity here, with, for consistency, gamma over 2m squared gamma replaced by kt over m. So this is kbt over m plus V naught squared minus kbt over m e to the minus 2 gamma. What is the variance of this process then? Therefore V squared of t minus V of t whole squared, this is equal to the variance of V of t. What is that equal to? So all I have to do is to subtract this out here, and then you begin to see, you see immediately that it is equal to kbt over m into 1 minus e to the minus 2 gamma t, because this term cancels. divides this, right. Now if I make the assumption that it is Gaussian, then we can actually write the solution down, the normalized solution down. What is the Gaussian probability density function look like? Remember that if the mean is mu and the variance is sigma, and then the standard deviation is sigma, or the variance is sigma squared, then the distribution density function is 2 pi sigma squared e to the minus the variable xi minus the mean whole squared divided by 2 sigma squared. That is the Gaussian, normalized Gaussian probability density function. So we copy that out, and therefore we can assert now that P of Vt given V naught must be equal to 1 over root 2 pi sigma squared, but sigma squared is this. So this is m over 2 pi k Boltzmann T into 1 minus e to the minus 2 gamma T to the power of half times the exponential of minus xi minus mu whole squared. So that becomes V minus V naught e to the minus gamma T whole squared. That is the mean value, which is a function of time. There is an m there divided by 2 k Boltzmann T Now of course it is tricky to show that at t equal to 0, as t goes to 0 you end up with the delta function, but it does so, because as you can see as t goes to 0 you drop this is V minus V naught whole squared, but this guy goes to 0 out here, and this fellow also. So you have a 0 from this whole exponential, and then you have something which blows up from here, and the result is a delta function in the limit, although it is not immediately obvious. As t goes to infinity, indeed it goes to the Maxwellian distribution, because this part goes away, you are left with this here, and this part goes away, that goes away, and indeed it goes to this. So this is certainly valid. And what will this distribution look like if I draw a picture? It would do the following. So as a function of V, if I plot P of Vt for a given V naught, at t equal to 0 it is a delta function, at V naught it is a spike, and then as t increases this broadens out, the average value, this thing is a symmetric distribution about its mean, which is at V naught e to the minus gamma t, and that slowly drifts. So you have something which looks like this, and then slowly drifts, and eventually at t equal to infinity it becomes the Maxwellian, and that is a symmetric distribution in this fashion. So the peak broadens and moves to the left, drifts to the left, and gradually hits this, and the variance changes with time like this, in this fashion. So variance starts at 0, which is delta function, and gradually reaches the value kt over m. Okay. This distribution function, this is called the Ornstein-Uhlenbeck distribution. We will take it from this point tomorrow, show you what happens next, but what we want to emphasize here is that this stochastic differential equation that I wrote down, the Langevin equation, is equivalent to a Markov process. It describes a Markov process whose probability density function, conditional density function, is the Ornstein-Uhlenbeck distribution. we will generalize that lesson to other stochastic equations. But this is in the physical context of a particle diffusing, and we will make further we will look at further consequences of this. Meanwhile, I would like you to check out the following, and that is not hard to do. It is the same integral that we did earlier, but now check out the fact that v of t prime in equilibrium, you could ask what this quantity is. We looked at v squared of t in equilibrium, we took the same v of t and squared it, but now you should take two different instants of time of this kind and ask what happens now. You could do this by finding first the average value of v of t prime, and then averaging over initial conditions, or by letting t go to infinity, t prime go to infinity, such that t minus t prime is finite. Either way you could do this, and the result, I would urge you to do it both ways. Write the integral down, and then you have now an integration over t1 and t2 which would be unsymmetrical. So if this is t1 and that is t2, perhaps t1 goes up to t, but t2 goes up to t prime, and your delta function constraint due to the white noise would be along this line. So what would contribute, you can replace, get rid of one of the integrations, but the other integral is constrained to be up to here and not up to here. So you can easily see that the smaller of t and t prime is going to be the region of integration for the second integral, whichever is left, the lesser of the two. So it turns out, if you work this out, this will turn out to be kt over m, that is the value at t equal to 0 times e to the power minus, well, you can almost guess what is going to happen. This is an equilibrium correlation function for a stationary random process, so it must be a symmetric function of the time difference, and there is only one constant of time here in this problem. Yeah, absolutely. So it is just e to the minus gamma modulus t minus t prime, turn out to be that. So check that out. So the Ornstein-Uhlenbeck process is exponentially correlated, it is not delta correlated. So by putting in the Langevin model, what you have done is started with a white noise which has 0 correlation time, but the driven or output variable has a finite correlation time, it is built into the system. So it says even though your noise maybe have 0 correlation, it is really instantaneous correlations, the output variable could slow down, could actually have a finite memory, and it does in this case. So it acts like a paradigm for random processes of this kind, and we take it from this point here, and I would like to, for example, look at the ordinary diffusion equation in the same language and ask what happens there. We will do that next. We will look at the displacement, we have not done that at all. We know that when these particles move around they diffuse, so I would like to look at the position variable and see what happens to the position here from the same model, and ask whether we can draw similar conclusions for this and connect it up with the diffusion equation and then more general stochastic equations. This is what I will do tomorrow. Okay, so let us stop here.